So yeah, welcome everyone to our 15th Sussex Data Science Meetup. As most of you will have attended before know, we're sponsored by a few different organisations. So we have Mojik here, who Colin Hayhurst is now the CEO of. Colin used to run these meetups. And Mojik's an independent search engine which, unlike Google, doesn't track any of your behaviour or what you're searching. So if you're looking for a more independent search engine, please try out Mojik. We're very lucky to be supported by Silicon Brighton, who host and run numerous other meetups and provide networking opportunities across Brighton. So Steve, I don't know if you wanted to say a few words.
Take myself off mute. Cheers, Pete. Yeah, hi everyone. Good to have you. Just following on from Pete, just want to say a massive thanks to everyone for coming along today. I think a fair few of you recognise quite a few new names, already know a fair bit about us, but just give you a bit of background for anyone new. To Silicon Brighton, our aim is to drive tech growth in our city, and we address that by hosting and promoting events where attendees leave with knowledge and skills gained and connections made to drive their careers forward. We also give the local meetup groups like Sussex Data Science a platform to promote themselves and have additional access to speakers, sponsors and attendance. And if there's a gap in the meetup space, we also help start some new meetups too. Hope everyone enjoys today's session. Huge thanks to Edward for joining us. And just on a final note, I'd say that we're really keen to hear from anyone who'd like to explore further how they can contribute to Silicon Brighton. Always in need of knowledge, speakers, loads of stuff really. So check out our website. It's siliconbrighton.com. From there you can join our community hub and you can reach out to me, Kieran, Kirsty, any of the team and find out how to get more involved. But thanks again for coming along.
Brilliant. Thanks, Steve. And the QR code there, if you scan that, that will take you to the Silicon Hub where you can find all the information about the different meetups and events Silicon Brighton are supporting. Okay, and finally, so I run the Sussex Data Science Meetup through my role in Discus, the Data Intensive Science Centre at the University of Sussex. So we're a research unit which gathers expertise in data science across the schools of maths and physics and informatics. So we help train PhD students in data science techniques, but also help people across the university who might have a data science challenge. And we're also expanding to work more with businesses where they might have a data science need. So we can do that through a variety of formats. That can be through things like hack days, who can explore a project quickly. As a research partner for grants, be it Innovate UK grants or Knowledge Partnership grants, traditional consultancy, and another avenue that a lot of companies are keen to pursue are student placements. And that can be with our MSc data science students or PhD students. So if anyone's interested, please just contact me. Okay, and then moving on to the main event you're all here for. So as Steve said, we're very lucky to have Ed Salakpi from the University of Sussex, and Ed's finishing off his PhD in the next couple of months. He's been working on the AstroCast project, but I won't go into any more details. I'll let Ed explain all of that. So if I hand over to Ed, and any questions, just post them in the chat and we'll get to them at the end of the talk.
All right, thank you for that. Let me share my screen and then I'll start. Okay, so can everyone see my screen now? Just give me a thumbs up if okay, right, yeah. Okay, thanks everyone for coming today, and also thank you, Pete, for the introduction. So to continue, well, like Pete said, my name is Edward Salakpi. I'm a final year PhD student at the University of Sussex, and I do my research mainly on trying to forecast droughts in grasslands or in shrublands, basically monitoring vegetation, condition using various, data-intensive methods in combination with satellite Earth observation data sets. And so that is basically what I do. And as a PhD researcher, I'm being supervised by Professor Seb Oliver and then also Dr. Pedram Rohani. And a lot of the work that I've been doing so far, I've gotten a lot of support from Dr. Pete Hurley as well. So today, I'll be talking about some aspect of my work and also some aspect of our research as part of the AstroCast project, which focuses on forecasting vegetation condition using some Bayesian methods. So to begin, okay. So my presentation will follow this outline. I'll first of all touch on some background as to what we mean by vegetation condition or drought, vegetation stress. After that, I would introduce, talk about how we use Earth observation data sets to monitor these vegetation conditions. Then I'll jump into our research that we've been doing at the AstroCast project, talk about the phase 1 of the research, and then the phase 2, which is what I'm currently doing. And then also talk about the forecasting work that I've been doing using the Bayesian models. And then from there, I'll show some results on how the model performed, trying to forecast some vegetation condition. Then finally, we'll look at the policy implications of some of the work that I've done, and then also conclude on that. And so I'll start with an introduction. By way of introduction, I first of all just want to give some background about what we mean by drought. So droughts, before I even go on, let me just even state that, I'll be interchanging vegetation condition and drought, because in this case, drought over here basically referring to, conditions of the vegetation in the field due to some rainfall or moisture deficit. So drought events are very prevalent. In fact, you look at a lot of news items, or you look online somewhere, you're always getting this information on drought disasters. And they are reported, almost yearly, happening at different parts of the world. But then when it comes to the definition of drought, it can be categorized into 4. We have some type of drought, or a category of drought called the meteorological drought, which is what is popularly known, which is drought resulting from rainfall deficit. We also have what they call the hydrological drought, which results from water deficits from streams, lakes, and various water bodies. Then we have what we call the agricultural drought, which sort of stems from it's like a physical manifestation of meteorological drought. And so this one is basically drought that occurs resulting from shortage of water in the soil that are available to crops and plants. And then when you then look at how all these droughts are impacting, human life, impacting you and I, then we come into this other last category, which is called the socio-economic drought, which is basically, as a result of maybe agricultural drought or meteorological drought, then we have some food scarcity or some food insecurity issues. But then out of all this, agricultural drought stands out because it has some form of direct connection to our daily lives, because, we all depend on some form of food or some form of, for food security, agriculture, because farmers are always relying on rainfall and also, soil moisture and other things. And as soon as, you have prolonged dryness or prolonged dry spell, then, agricultural drought sets in, and then it affects food security. So, this happening? Oops. So, like I've said, the devastating effect of agricultural drought is seen, everywhere. But then when you come to Africa and some developing countries, like in the eastern corridor of Africa, you find out that it's very prevalent in the semi-arid and the arid, regions. And in these regions, the livelihood of people depend mainly on pastoralism or agro-pastoral. They practice a lot of agro-pastoral, activities. So they're either growing some livestock or, having some farm on the side. Now, usually what happens is that these animals rely heavily on, the grasses in the fields. And then the people themselves also rely heavily on their crops in the field, actually, because that's what actually drives the economy in some of these ASR regions. But then anytime there's a prolonged dry spell or there's drought, these shrublands and grasslands that serve as, the main fodder for the livestock are the first to be hit by, these prolonged drought spells. And when these things happen for a long time, it usually leads to, loss of life, loss of livelihood, loss of income for the affected communities. And so these are the challenges that come across whenever you have these prolonged drought conditions. So what then is the way forward? The way forward has always been, coming up with a system that could, anticipate these drought events before they happen. So people have proposed the early warning systems as a way forward. And even, global initiatives like the UN or the Paris, climate change initiative, they've all recognized that, early warning systems are important to, solving the drought problem that, faces the world on a yearly basis. And in fact, the UN have also come out to say that, having this early warning systems in place is 20 times more cost effective than, preparing for post-disaster relief. And so early warning systems are the way to go. But then some of these early warning systems require some very complicated infrastructure, for collecting and analyzing data before you be able to get some good warning. And most of the developing countries don't have access to some of this infrastructure because of, the cost component. But, recent advances in technologies are making some of these things easier. One such is satellite Earth observation. So satellite Earth observation, basically, we have satellites in space, constantly taking pictures of the Earth and making such data available freely. And so some of these data sets are available freely. And because of the growth in, the technology space and advances, some of these things are becoming very accurate in capturing, ground data and making this information available. So the data collected by some of these institutions like the European Space Agency, NASA, the United States Geological Survey, all these data sets are made available and they are free to access anytime. And so it makes it now a bit cost effective, to implement some of these early warning systems for these resource poor communities that are faced with drought on a yearly basis. Now, what are some of the data sets that we can get from these Earth observation instruments that are in space? So they provide, the data on temperature, on weather and climate data, so rainfall, precipitation. Also, we also get data on vegetation health from some of these satellite images. And even recently with the European Space Agency Sentinel-5, I think, they've also started releasing their data that is on, carbon emissions and methane gas emissions. And so all these things make it possible to monitor things that are going on the surface of the Earth, to come up with systems that could help, save the Earth and then also, stop this climate change that we are currently talking about everywhere. Now, drilling down to my work or our work here, which is vegetation, monitoring vegetation and drought. How do we apply these satellite images in order to monitor these vegetation conditions? So these satellite images, these satellite instruments actually take pictures of the Earth in various, electromagnetic wavelengths ranges. And this ranges from the red, the near infrared, blue, green. So data is always captured in some of these bands. And every band has some unique information that it gives concerning what is captured on the Earth's surface. So when it comes to vegetation, which we are interested in, if you look at this plot over here, you can see that vegetation is this green line. And you can see that vegetation is very, very key. I mean, it comes out clearly in the near infrared, band. So when you plot it across the various bands, the red, blue, green, and the mid infrared, you see that it's very prominent when it comes to the near infrared. So it means that a lot of the information on vegetation is captured in the near infrared band, and then also somewhat in the red band. And so what we use this information to do is to calculate some vegetation indices that tells us, the health of the plant on the ground. And so using the near infrared and the red, and putting it in this formula, you should be able to come up with this vegetation index called the Normalized Difference Vegetation Index. Now, this one is basically that whenever the plant is healthy enough, it reflects, a large amount or a high amount of near infrared and a low amount of the red band, in the red band. And when the plant is not healthy, you get a low, near infrared and also somewhat higher red band. So if you put this two bands, information from these two bands from the satellite image into this formula, you derive what they call the Ndvi, which basically tells you the level of or the health of the plant. And this value usually ranges from -1 to 1, where the negatives usually depict water bodies and non-plant items on the ground, and then anything ranging from probably 0.1 all the way to 1 positive. It's mostly depicts vegetation on the ground. Now, having this Ndvi alone doesn't give us much information on the drought condition, at a particular area of interest. And so what we do is we usually just also use this Ndvi and combine it with some long-term minimum and maximum of Ndvi. And, we compute what they call the Vegetation Condition Index, or the VCI. Now, the min and max here that we use are usually, I could say it as a long-term min and max, or seasonal min and max. So if, for instance, I wanted to compute VCI for 17th, it's like, let's say the 3rd week in June, then I'll take Ndvi for the 3rd week in June, and then look at the minimum and maximum for all 3rd weeks in June across some baseline period from maybe 2000 to 2008, or from the year 2000 to 2018, where, we've had we have some drought events occurring. So we put that in this formula, and then we come up with this index, which is called the Vegetation Condition Index, which gives you, which quantifies the drought condition in a place given some Ndvi value. So these are the steps. We start with the Ndvi, and then we calculate this VCI, and then we try and understand what the VCI values are. Now, the VCI values, you can see that whenever we compute this, we multiply by 100. So we have these values that range from 0 to 100. And each level tells you some information about the drought condition on the ground. And so whenever you have a VCI ranging between 0 and 150, then you know that probably, we are experiencing some wet conditions in the place. If you have VCI, ranging between 50 to 35, then you know that, you have some normal condition. But then anytime the VCI falls below 35 and below, then we are talking about a drought, or vegetation stress or drought occurring at this particular region of interest, or you have, moderate to severe drought occurring in that area of interest. And so this is how we measure the VCI, and this is what the VCI tells us. So in our work, we just try to use this indicator to monitor what is happening on the ground in terms of vegetation condition and also drought, and then try and use, the persistence property of this VCI to see if we can forecast future scenarios and so we can create this early warning system that will forecast this VCI value, so we can, inform farmers or pastoralists in time as to what the vegetation condition is likely to be, maybe in the next 4 weeks or in the next 6 weeks or the next 10 weeks. So what have we done so far? So far in our research as AstroCast, we've used this Vegetation Condition Index, VCI, with some, advanced modules like the Gaussian process and then also the Auto-Regression. We've used this to come up with some forecast models that are able to forecast the VCI. Just to give you a little bit of background about how this Gaussian process works, basically is a model that you give it a time series of the VCI that we are interested in. It learns the covariance between the successive points and then uses that covariance information that has learned from these points and try to, extrapolate or guess what the next VCI value is likely to be. So we give it data up to maybe June 2021, and then we ask it to give us June, July, August, give us July, August to December, that kind of thing. So it makes this extrapolation based on what it has learned from the historical data. Now, this model has we've gone to our stakeholders, which are mainly in the East African region, especially in Kenya, and we've showed them this, and they fell in love with this, and they've actually started implementing this in their systems. And so also, to report on, so as part of, reporting on other drought conditions, they've also added the Vegetation Condition Index, forecasting of Vegetation Condition Index as the monthly report that they produce for, stakeholders or even farmers in their regions of interest where they want this information to get to. But then the thing is that with this model, yes, we're able to produce very good forecasts values, but then the accuracies were very good for only short range forecasts. Now, most of these relief actions, rely on this information so that they can take some action. But then when you give them short range forecasts, then they don't have that ample time to prepare enough, to attend to the action. And so we found out that the short range forecasts were not going to be enough for them. And so we thought of, extending the forecast range. And so that brings us to phase two of our work, which is what I'm going to talk about. And so we know that the Ndvis and the VCIs are affected by other variables apart from themselves, apart from the persistence in there. So we know that they are affected by precipitation, soil moisture, and then also temperature. And so we ask ourselves that, can we, improve our forecast models, or can we extend our forecast ranges beyond, the current range that we have by including these additional variables into the model? And to achieve this, we decided to use data from so many places and, bring in this additional data sets that we know that affect the vegetation condition in a particular region of interest. Now, most of the work was done in Kenya. In fact, all of the work was done in the arid and semi-arid regions in Kenya. So data was sampled from these regions and used. And the data set that we used included, precipitation or rainfall data, which came from CHERPS. CHERPS is basically a climate hazard group that produces rainfall data using a mixture of on-ground data and also the cold cloud duration rain estimates, which are based on remote sensing satellites. And so they also make this information available as remote sensing data sets that you can use for, analyzing and, looking at rain and rain forecasts and other things. Now, we also brought in soil moisture. Now, the soil moisture data, that's the interesting bit. I know a lot of you would ask, how would you get soil moisture from satellite images from space? Well, with the use of synthetic aperture radar or radar satellites, they are able to capture and retrieve soil moisture from the surface of the ground. Now, these radar satellites emit, microwaves onto the surface of the Earth, and then they capture the backscatter or whatever is bounced back to the satellites, and then they capture that backscatter of the microwave that is reflected back onto the Earth, and then feed those backscatter that they've collected into an algorithm, and the algorithm produces some soil moisture values based on some models that they have. And these data sets, the soil moisture data set has been verified with some on-ground data, and they found out that it correlates very well with some online or from some on-ground data. And so that is why we chose this European Space Agency Climate Change Initiative soil moisture data. Now, the temperature, we decided to also use land surface temperature, which is also captured using, it's produced by NASA using the MODIS, the MODIS products. And this land surface temperature is actually derived from what they call brightness temperature in the thermal band of whatever images they capture of the Earth. And so they convert this brightness temperature into temperature in degrees Celsius that you can use to measure the land surface temperature. And then finally, we also use the near infrared and the red band, which I spoke to you earlier on, converted that into Ndvi and also converted that to VCI. And these ones were also taken from the MODIS products. And this time we use the MCD43A4 product. Now, from these images over here, which are the processed VCI images, you can see that there are some white regions here. There are some gaps over here. Now, these gaps mainly resulted from cloud cover. So this is one of the challenges you have with using satellite images. You always have to deal with cloud cover. And so whenever you correct or clean your data set by removing these cloud covers, then what happens is that you lose a lot of data in there. And so one of the pre-processing we had to do after this is to find a way, to temporarily fill these gaps. And so that is one of the pre-processing we did. We cleaned the data by removing clouds, and then we filled in gaps by using some interpolation methods. So the methods that we used to be able to achieve this was the Bayesian auto-regressive distributed lag model, which enabled the inclusion of additional variables. So, and then as a baseline method for which, we compare our results from this BRDL model to, we also use the auto-regression model that was used in our earlier work, also on our data, so that we can compare our results and see how well, if the additional variables are making any change or not. So just to take you a bit into the auto-regression distributed lag, what are they? So basically, they're a generalized form of the auto-regression model. So the auto-regression model is basically a model that, learns from the past values of a particular variable you're interested in. So if, for instance, you wanted to forecast future VCI values, you learn from past values of the same VCI. You put that in the model, in the AR model, and then you use that to make your forecast. But the ARDA model allows you to also, apart from the dependent variable, the variable you're interested in, allows you to also bring in additional explanatory variables. And so basically ARDA, like I said over here, enables you to model as a function of its own lags and the lags of additional, explanatory variables or the independent variables. So the dependent variables in our case here will be our VCI, and then also the soil moisture, temperature, and the rainfall that we are bringing in will be this. But in this case, we are going to use the lags of them. So we'll look back and then use the lags of those values in the model. Now, mathematically, this ARDL model is represented as, ARDL. They just put some values here, P and Q now. This P actually is the number of lags of the independent variables. So if you're bringing in soil moisture, rainfall, then, you need to look at soil moisture maybe 3 weeks ago, 2 weeks ago, and then a week ago. And then also look at rainfall also using the same lags. And so this P represents the number of look back, the number of times you want to look back. And then the Q over here is the auto-regressive part, which is, the number of lags for the dependent variable which you're interested in, which is the VC. In this case, would be the VCI itself. And so representing this as a regression problem, you see that this, for instance, a dependent variable, which is a future value, you want to forecast, which is the drought index at the future value at the T plus I. And then over here, we have our dependent variable, which is the VCI that we are interested in, which is the lags, T minus 1 of the VCI, so the lags of this variable that we're interested in, together with their regression coefficients. And then also we can bring in the lags of the independent variable, which the additional dependent variable, which in this case are the rainfall, soil moisture, and the things you wanted to add. Now, just to give you a bit background, or just to explain what some of these variables mean. And so if you look at the equation, basically what we are saying here is that this beta, and all these other values here are actually the regression coefficients of our data sets that we are going to be, or of our data that we are going to model the ARDL on. And this one here is going to be our intercept. So you can see the definition of these parameters here. And then also we have an error term over here, which we assume to be a normal distribution. Now, to make this a bit simpler, I tried to, rewrite the equations where all our data sets, which is the X for the lags of the drought index, the VCI, the X for the lags of precipitation and soil moisture and temperature, will all fall into this X over here. And then I bring all the coefficients into this beta over here, just to rewrite the equation to make it a bit simpler. So that in the subsequent slides, you can just follow how this thing works within the Bayesian context. So why did we use the Bayesian? Why are we doing this, the Bayesian concept, and not just fit in the equation that I showed earlier on, directly in with some maximum likelihood, just to get some, regression coefficients and then use that for our predictions? Well, if you use just the maximum likelihood methods, you end up, getting point estimates. So you're going to get only one value for your beta, and maybe one value for your alpha and all those other parameters. And usually these frequentist approach, or these models that do not use this Bayesian methods, often results in, the case where you always have overfitting, or you have your model, producing some imprecise predictions because the point estimate maybe is not adequate enough to, make your predictions. And so we try to do this within the Bayesian framework. Now, within the Bayesian framework, it allows you to, first of all, incorporate, your prior knowledge. And so if maybe you are an expert in the field and you know that, okay, the regression coefficient, maybe you've done this several times and you know that maybe the regression coefficient will range between a value of A and B, then you can pass that information into the Bayesian framework. It allows you to incorporate prior knowledge. And then if you don't have that prior knowledge too, it allows you to also, give in some week prior that, you don't have. You can also assume that I don't know anything about it and also give it a weekly informed prior. And then it would also look from the data and also infer the adequate parameters for you. Now, the other thing is, and these parameters, the parameters from using the Bayesian model also approximated using the Markov chain Monte Carlo algorithms that sample from a given parameter space that is based on your prior knowledge that you've given to it. And then the parameters that you get out actually, which is in this aspect, is called, in this case, it's called the posterior, come as a probability distribution. And so instead of having a point estimate of your beta variable or your beta regression coefficient, you get a distribution of the coefficient. So you get a distribution that has maybe 1,000 values in there or 2,000 samples in there. And then using this usually gives, more precise predictions. And the best thing about using this approach is that it allows you to easily, quantify the uncertainties on your prediction. So you can always say that, okay, I predicted the value for today to be this, and it lies within this confidence interval or something. It makes you to easily quantify that. So let me just take you a bit into the mathematics, not too much into details. So how do we get this, framework, this ARDL into the Bayesian framework? Now, the Bayesian framework, as some of you might already know, is basically a conditional probability problem that we are trying to solve over here. And so we are trying to look at, the probability of this theta here given some x value being equal to the probability of the x given some priors, and then also the probability of the x itself. So that is the Bayesian formula over here. But then how does this fit into this Bayesian formula? And so if you look at the definitions over here, what we are trying to achieve is that we are trying to find the probability of our model parameters given our data. So that is what we are trying to find the parameters. But then to find that, we need a likelihood function. And the likelihood is the probability of your data given some prior parameters, So you give it some parameters and then you give it some data and then you give it some prior, and then you want to find what the actual parameters are based on your prior. And then the priors are your belief about what the parameter is likely to be. Now, the last factor here, which is the probability of the data, is a normalization term, and it's usually very difficult to compute. And so usually the equation is rewritten as this, where the probability of your parameter given your data is proportional to just the likelihood and the prior. So we take out this. But then because we've taken out this and because this is very difficult to compute, then to get your parameters, we fall on the Markov chain Monte Carlo algorithms. And in our case, we use the Hamiltonian Monte Carlo algorithms. Now, over here, I will not go deep into this, but then we use those algorithms that actually are able to go to some sample space that you've given it and then sample parameters based also on the data that you've given to it. So to bring this into this is what it looks like. So for me, the prior belief I had about our data was that our alpha is distributed as a normal distribution with a mean of 0 and a standard deviation of 1. Now you could use any value based on your belief about the parameters, or if you don't have any knowledge about it, you could also use, very weakly informative priors that then you leave everything to the model to actually learn the parameters on its own. But in our case, we are working with lags, and with lags, we usually have a strong correlation existing within the lags. And that is something that we try to avoid in this machine learning space. When you have the strong correlation within your variables, then you end up you end up not having models that will be able to predict your target variables very well. And so to control that, we use smaller, we use some weakly informative priors here. So we try to use, smaller, what they call the regularized priors, so that, we get parameters that do not correlate too much within themselves. And then for our likelihood function here, we then pass our ARDA model to that. And so what we are saying is that to actually see how our data is going to be given some parameters, then that is going to be distributed as a normal distribution that takes in the alpha plus the beta and then the lags of our input variables, and then with the standard deviation being our error term. And so that is how we put this into this. And so using this model, then we pass this to the MCMC. The MCMC then goes to some parameter space based on this priors and then tries to approximate or infer our model parameters. Now, to do that, we actually use some form of a cross-validation. So in time, when you're dealing with time series, you cannot use the regular cross-validation where you just, cut off your data, maybe some 70 and then hold out some 30 and then, train on the 70 and then forecast. It's best to actually, do some form of a rolling window cross-validation where we have a time series that ranges from maybe this point to this point. You take a chunk at a time, train the model on that, make your prediction. Take another chunk, train your model on that, make a prediction, take another chunk. And so this is what we did. And so the results that I'll be showing subsequently are all based on this kind of results from the cross-validation that we have evaluated. So having trained our model and produced our forecast, then we now come to the results. So just to give you a slide picture so you understand what I mean by the Bayesian models giving us distribution, not point values. This is how a 6 weeks ahead, for instance, forecast looks like. So whereas in a frequencies approach or in a regular approach without the Bayesian framework, you're just going to get 1 point value for maybe you're going to make a prediction, you're going to get maybe just a value of maybe 40 or maybe 35 or something. In the Bayesian model, you are getting a distribution of forecast, which ranges from somewhat 20 to 70. And so you know that, okay, and then when you find the mean of that, then the mean is going to be your mean of your forecast or your prediction, which in this case is represented by this. And then we also have the observed value. That is the value that, because we're training the model on data that we've already observed, we can compare whatever we've predicted to observe just to check how well our model is predicting. And so this line over here represents that. And then this, like I said, represents the distribution. And then we can actually also look at maybe the 95th percentile, right? The upper level of our 95th quantile and the lower level of our 95th quantile of our forecast distribution. So then we can say that, okay, we are forecasting that 6 weeks ahead, we're going to have maybe 49, maybe we are predicting maybe 48 or something VCI within a confidence interval of this. And so that is what we mean by we are getting, some forecast distribution from our posterior parameters that we have, inferred from the data. So just to give you a broad overview of what the results look like when we trained our model and made our predictions. So on the top here is results based on the auto-regression alone, where we used only the VCI without including any additional variables. So what we have over here is, we just want you to, first of all, pay attention to the the correlation between the true VCI and the forecast, and then also the R-squared value here, which is more of like giving us information on the sort of accuracy of the module. And then compare that to the ARDL as well. So you should look at the R-squared value. So looking at it, you could see that, yes, for the AR even, for instance, you could see that, yes, true VCI correlates very well with the forecasted VCI with a very good R-squared value. And the R-squared value usually ranges from 1 to 0, where 1 is good, and then as it goes to 0 is very bad. And the R-squared is basically just telling us how much of the variations in the observed were captured by the by the predicted models, right? So what variations in your observed values that are being explained by your forecast or by your forecast module. And so here you can see that for 4 weeks ahead, yes, we are getting some good accuracy over your R-score of 96. And with the BRDA model that had the additional variables, we had slightly higher R-square values. But the interesting thing is that if you look at the R-square value, for instance, for 6 weeks ahead, and you look at the R-square value for 8 weeks ahead for the BRDA model, you see that scores that we are getting for 6 weeks ahead, we are now getting for 8 weeks ahead, which means that we've gained an additional 2 weeks of accuracy with the BRDA model compared to the AR model. And you could see that, across, even for 8 weeks ahead, when you're getting 0.77 for the AR, we are getting 0.74 at 10 weeks ahead. And so, yeah, we can say that, yes, we've gained some additional weeks by bringing in the additional variables. Now, just to drill down a bit on how the metrics look like. So here I'm just comparing the root mean square error, which looks at the deviation or the average deviation of your forecast or your forecast data from the observed data, right? And that is what the RMSE looks like. So how far is your forecasted value from your observed data? And so a smaller value means that, yes, it's not, the forecasted value is very close to your observed value. So which means there's a higher accuracy over there. And as you go up, it means that, your error is getting bigger and your forecast values are not, too close to your observed values. And so you can see that the R-square values remain, the R-square value for the BRDL remains low compared to the AR model across the various forecast lead times. So for up to 10 weeks, you see that the BRDL model remains low. And then for the R-square values, that looks at the variation in the observed that have been captured by the module. You see that the BRDL also seems to capture a lot more variation in our observed data compared to the AR model. So you can see that across the forecast horizons, the BRDA model, performed better than the AR model. I keep talking about being able to quantify uncertainties and, explain, the confidence interval and other things using the Bayesian model. So over here, I just try to show how, we can actually analyze that uncertainty that our model is able to produce, the BRDA model is produced. Now, doing that, I used some metrics called the prediction interval coverage probability. Now, this metric basically measures how often your observed variables lie within the credible interval of your predicted value, or your forecasted values. And that is mentioned by the PICP. Now, the PICP, best PICP should range between, 0.9 to 0.99, or even above that. But then it doesn't always mean that your model is accurate. What actually helps you to know if your model is actually precise is the other one, which is the mean prediction interval width, which gives you, the width or the distance between your upper level and your lower level. And so from these two plots over here, you can see that for the AR model, you can see from the PICP that a lot of the time you don't have your observed values lying within your forecast, your forecast interval. But then for the BRDA model, yes, we are getting about 0.99% of the time you have, our forecast. So here we're just trying to see how well, our forecasts are precise, or how close they are to the observed data, and also check the error and also give us information on the error on the prediction. So over here, you're seeing that the error on the prediction for the AR models are quite larger compared to the BRDA models. I would like to just also say here that I've said from the beginning that it's easier to quantify this, errors with the BRDA model, because they give you this, forecast distribution. Over here, to compute this, I actually had to use the RMSE that I got from my AR, and then and then the 95% Z-score of the standard normal distribution. That is what I used to compute this confidence interval. I did it just so that, we could actually compare what the confidence interval for a frequentist, approach will look like compared to the Bayesian model. And overall, you could see that, yes, even for this, I'm just showing for 4 and 6, you could see that the BRDL model performs better with lower, error compared to the AR method. Now, next is, fine. I mean, you are producing some VCI values, but then how do you measure if your VCI value is actually, or your model is actually forecasting a drought condition or not, right? So to assess that, we had to go into a bit of the classification, phase. This problem here is a regression problem, but then we have to go into a bit of classification where we are trying to, look at whether each prediction depicts a drought condition or a no drought condition, right? And so to do that, we use some threshold of VCI 35, VCI less than 35. Now, this VCI less than 35 was chosen because the stakeholders that we work with from Kenya use this threshold to, to trigger whether there's a drought event occurring or not. And so we also based our models on that threshold. And so we said anything below 35, we classified as drought. Anything above 35, we classified as no drought. And then what we did with that was to plot what they call the ROC curve. Now, the ROC curve is basically just, first of all, telling us how well our model is able to predict some drought condition. And when it predicts that drought condition, what is the probability of that drought condition being true and the probability of that drought condition that is predicted being a false alarm? And so if you look at our ROC curve, for instance, you can see that if you take for the AR model, anytime we predict that VCI is below 35 using the AR model at maybe 6 weeks ahead, this line here represents the 6 weeks ahead, then 86% of the time is true. But the probability of that being a false alarm is 10%, which is quite good. But then if you look at the ARDL model, you could see that there was some improvement, right? Where with a 4%, sort of a 4% improvement, where the hit rate for the ARDL model is 90, and the probability of that being a false alarm is just 7%, which means, we've drastically, or not drastically, but we've somewhat decreased the probability of, having false alarms within our forecasts. And so over here, you could see the various values, that is percentages for the various, lead times for the various models that we use. So for the AR, you can see that whereas the false positive here is 6, here we are getting for 3, and then you can see that generally you can see that the BRDA model performs better than the AR model. Now, the next thing we also looked at is, since we are doing forecasting, then we thought that then it would be appropriate to actually go into, apart from giving some forecast value, also give some probability forecast. So, you forecast maybe a VCI of 46, and then you're saying that, okay, that 46 has the probability of, or has a chance, or has a 98 or 80% chance of happening, right? Just like what we see with the weather kind of forecast, So we try to also compute the forecast probabilities because we once again have some, forecast distribution. So using this forecast distribution, we can calculate some probability of the based on some threshold. In this case, we're still using the VCI less than 35. But then how then do we, assess the quality of our forecast probabilities? For that, we used what they call the reliability diagrams, where you take all your forecast probabilities, you bin them into, in this case, I bin them into 0, from 0 to 0.2, 0.2 to 0.4, all the way up to 1. And then for those bins, I look at the observed values that were true for those forecast probability bins. And so over here, what you're seeing is that anytime maybe we forecast that there's an 80% chance of there being a drought event of VCI less than 35. Comparing that to observed data, if maybe I take, let's say, 6 weeks again, or maybe 4 weeks, if I forecast at 4 weeks that there's an 80% chance of a drought event occurring, then that actually happened about, I would say, 89% of the time, right? And that was observed 89% of the time in the observed data. So this is how we also actually measured the accuracy of our forecast probabilities, or the scale of our model being able to forecast, accurate probabilities. And from the sharpness, you could see that the sharpness value diagram over here basically tells you the frequency of the forecast that fall within a particular forecast probability. So here we can see that we are looking at a binary event, right? We are looking at was there a drought, yes or no? Now, when you look at the yes, you're seeing that a lot of the yes were forecasted at a probability of almost, I would say, 100, maybe 90 to 100% forecast probabilities. And so we could see that for 4 to about 6 weeks, or even somewhat 10 weeks, we're seeing that our model is producing, very high accuracies for the forecast probabilities. So this brings us to the end of our model assessments. Now, so overall, we've seen that yes, bringing in these additional variables have improved our models. So what then are the policy implications? So over here, you can see that from what I've said so far earlier on, you can see that the probability distribution of the forecast from our BRDA model will enable effective risk analysis, because here you are having some forecast distribution, and so you can take much more informed decision on whatever forecast values that you get. And the forecast probability that we produce from our models also would help inform the people in charge of addressing the drought, or sending relief efforts to drought affected areas. Will help them inform on which drought alarm to work on, because probably you might get some alarm but with a low forecast probability, but you might get some alarm with a high forecast probability. So then in this case, you are inclined to work on the forecast with a high probability. And then for most of these people, they work with some model which they call the forecast-based finance. And so you trigger some action based on some forecast threshold. And so with this kind of Bayesian models, then their management of the forecast-based finance initiatives becomes easier. So in conclusion, we have seen that yes, the additional variables improved our model. Our forecast ranges from up to 10 weeks. We could see that. And then also, modeling agricultural drought within the Bayesian framework is a better option, as you can see, for decision making. And then also in terms of cost effectiveness, we can see that yes, with cheaper access to data now, and with this models, where it doesn't take much to implement them on some server, but then you have access to some free data, and then with this BRDA models, you can easily implement them, and then without incurring so much cost. And so we think it's a much more cost-effective approach to monitoring and forecasting rangeland droughts for stakeholders or target users with limited resources. So that brings me to the end of my presentation. Thank you very much.
Thank you very much, Ed. That was brilliant. There's been a bit of a lively discussion in the chat, which is really good. So we've got a couple of questions, which I'll give to you in the last couple of minutes before I make a few more announcements. So one question from Oscar was, in terms of the early warning systems, I guess you might have covered this in one of your last slides, but what type of actions can they actually take if a region's headed for drought? And can you actually ship water onto site in meaningful quantities, or what other actions can you take to help those undergoing droughts?
Yes, so for the drought relief agencies in Kenya, for instance, what they do is, so like I said earlier on, they work with this forecast-based finance initiative kind of thing. And so they have the system that is triggered whenever you get some VCI value below the threshold. So as soon as that is triggered, then what happens is either they reach out to the farmers, maybe buy out their livestock and give them money so that and then take the livestock from them, or provide them with some money that cushion them while the drought period is still active, or anticipating what is likely to happen. Then they give them some money, or even go and buy off their livestock. So those are some of the actions that they take.
Okay, brilliant. There's a question from Mark Harrison, who I think unfortunately had to leave, but it's an interesting question. So it's, given that the data series related to time of year, is there analysis of whether predictions of different models are more accurate in certain seasons?
Yes. So that is key. In fact, you can see from this slide, for instance, where I look at how well the individual variables contributed to the VCI forecast. You can see that for the March, April, May season, you can see that yes, rainfall is contributing more to forecasting VCI than the October, November, December season. So yes, so there's some seasonal component to that as well.
Okay. See, Colin's got his hand up. So Colin, I know you want to take yourself off mute and ask a question.
Yeah, Edward, excellent, very interesting presentation. The question I had probably doesn't relate to your work. I guess it's more about people who came before you, but I was just fascinated right at the start. You had the VCI measure in the denominator. You had the max and min values of the NVDI, is it? I guess.
Yeah.
And whether that matters, and whether I don't have people looked at whether you could use 10% and 90% levels in the denominator. Am I talking rubbish?
Well, yes, a lot of concerns have been raised about the VCI formula, actually. Yeah, but then we've not tried to address those things because because this is what has been in use for some time, and so we just try to toe that line. Yeah, but then a lot of, especially mathematicians who've seen this formula, usually raise questions about it, whether it's not the appropriate kind of way to compute the VCI. Yeah.
Brilliant. And there was questions about Azish. I think some of them been a bit of discussion about the use of synthetic aperture radar data. So I guess a more general question about whether you could use it to help fill in the information when you're missing from cloud cover.
Well, yes. I mean, when it comes to the cloud cover challenges usually come when you're looking at the reflectances for computing the vegetation indices. So in that case, then yes, I mean, I know of some works where people have used, synthetic aperture radar as a way of filling in, cloud cover. Yeah, so that is something, but then we've not explored that yet, but I know of works that are going on, using that to fill in the gaps. Yeah.
Okay. And one last question from Archie. It's, how do you deal with the different growing times of different crops over short periods?
Well, in this particular work, we didn't consider, the phenology of crops. We're just looking at grasses and shrublands in, rangelands where people pastoralists usually send their animals to go and feed them. So we didn't consider that in the model yet. But then in future work, yes, we are considering some models that will actually be able to, in fact, it's something I'm currently working on where I'm using some hierarchical models to learn different parameters for the crop regions, for the grass regions, from the shrub and maybe forest regions. Yeah. So that is what I'm currently doing, using hierarchical models. And so from that, I should be able to answer that question.
Brilliant. Well, thank you very much, Ed, again. If I just grab the screen share off of you, just to go through the last few slides before we close up. Okay, so just before you all leave, just a few quick announcements. So there's a few up-and-coming events hosted by Silicon Brighton. So we've got the Brighton Java on the 22nd of June, the PHP Sussex meetup on the 29th of June, and Brighton Pi on the 8th of July. So strongly recommend you sign up to some of those. I'm sure there'll be interesting events. We've got a QR code there to scan to take you to some of those events on the Silicon Hub. And then just a reminder that the talks here we're putting up on YouTube, so you can watch in your own leisure again later on. And the slides I'm putting up on the Silicon Hub or the Silicon Brighton Hub, so you can go and look at those slides as well. And then that just leaves me to say thank you very much for coming. We've got a date of the 19th of August for our next meetup, still to confirm a speaker. So if you're interested or you know someone who'd be great to speak at one of these events, then let me know. Otherwise, thanks for joining, and hopefully see you all soon in a couple of months.